good day, ladies and gentlemen. This week we are going to talk about one application of differential calculus, or how we apply differential calculus in the theory of production. My name is Daniel Kabna Trefo. The overview, we will have a good definition of what a production function is, and look at how to differentiate concave functions, concave or convex production functions. We will discuss the marginal rate of technical substitution, and then we will talk about elasticity of substitution. This is the outline of the session. The reading list is the same. Please take your time and look at these lists. Now, what is a production function? Now, it's when you look at a production function, it's a function that shows mathematically the relationship between the quantity of outputs inputs that a firm uses and the quantity of output that it produces out of that inputs. And if we look at a very simple function as we have over here, like you're producing K from, let's say, x1 and x2. X1 can be Cont'd, x2 could be water. In our simple example, we assume that whatever comes out is positive. Okay, the inputs to are all positive, and these are standard sort of assumptions that we make in economics. What we need to do is to know the total product, average product, and the marginal product, of an input, and then know the relationship between them. When you talk about the total product of an input, let's say x1, is the quantity of the output that can be obtained from the input if the other input is held constant. So in our total input here, you have your x2 here being a constant, and you have your x1 over here. In the same way, when you look at an average product, it's just the total product. Let's say average product of input, let's say x1, is the total product. X2 is kept constant, and then divided by the x1 over here, which is the variable. In the case of marginal product, we're talking about the derivative, right, of the total product function with respect to x1, while x2 remains constant, and we can have a function of this nature. Now, one thing we need to know is that in the production function, the marginal product is equal to the average product at the maximum of the average product. And therefore, when we try to more or less understand this concept, we have here to be the marginal product, and then we have this one to be the average product. It implies that since the marginal product is equal to the average product at the maximum of the average product, means that we have to differentiate the average product. And when we differentiate the average product here, we are using the the quotient rule. We get this, and when we equate it to our marginal product, multiply through by x0, and reorganize this equation, we have we obtain what is over here. And the reorganization gives us the equation that we have over here. So what is left on the left side is the average product, and we have this marginal product here being equal to the average product at the maximum of the. So we have proved that we have really proved what we've done here is to show that the average product is equal to the marginal product. We were supposed to show that, and with this equation here, we have been able to show that the average product is equal to the marginal product at the maximum of the average product. Now, what we also talk about output elasticity of input. So the output elasticity of input, right, which I will denote by Wi, of input x1, right, with respect to our function, is defined as the proportionate rate of change of V with respect to xi. Mathematically, what it means is that we have to take the differential of the natural log of these functions, and this gives us the relation we have over here. And when we reorganize this equation, okay, we get the output elasticity to be equal to the marginal product divided by the average product. There is one important relation that we can draw from here, that If the marginal product is greater than the average product, then the output elasticity is greater than 1. If it's less than the average product, then the output elasticity is less than 1. And when they are equal, so it implies that the output elasticity is equal to 1. So knowing the marginal product and the average product can tell you the nature of the output elasticity of a production function. Now let's look at an example. We have this function over here, and our aim is to find the marginal and the average product, and also to find the value of the first input x1 with respect to average product, and then the marginal product will be equal to 0 if the value of the second input is equal to that. Now further, we have tried to show the solution over here. You can take your time systematically and go through and be able to convince yourself that these are the solution to the examples that we have over here. There are some activities for you here following from what we've done over here earlier. Try and take your time and do these activities, and let's meet at the chat room if you do have any problem. Now, one important thing that we need to do is trying to investigate the concavity or the convexity of an isocont. Recall that an isocont is the locus of all combinations of inputs that yields a specific level of output. So what it means that if you assume your output level to be constant, right, how would you value your inputs to be able to achieve that same level of what output level that you want? So in this case, what we can do is that if you look at our multivariable function f, right, where we have our f depending on two variables x1 and x2, and if we allow our output here to be constant, if this v is constant, definitely we can express one of the variables in terms of the other. And specifically here, we have expressed the variable x2 in terms of what x1. Once we make this one allow the output to be a constant value. Now what it means is that we can now decide to plot our isocont, which you are quite comfortable or have met this before. Now the gradient of this isocont you know is negative, because as you increase one input, you have to reduce the other in order to ensure that your output level is kept what? Constant, right? So if you are located on this output level, whenever you reduce this, okay, from B to D, that is input x2, you also have to increase, right, input x1 from C to A to be able to achieve the same level of, isocont. And these are some of the main sort of characteristics of an isocont. It's a convex, as you can see over there. One thing that we do talk about is the marginal rate of technical substitution of an isocont, okay? So like if you are trying to move along an isocont, how much do you reduce one input and how much do you increase one output in order to more or less be at the same level of what production or output level? So what it means is that in order to do that, we have to take the first, derivative of the second input with respect to the first input, and that gives us the marginal rate of technical substitution. And what happens is that when we take the first derivative of that function, we have what we get over here, okay? And the simple reason is that we have a negative because as one increases, the other should decrease so that we can assume the same level of output. When we take the second order derivative, so this is our first order derivative, we take the second order derivative and then we can also express it in this way. And what do we get? We are going to get, you can easily convince yourself that the second order derivative will give us what we have over here. Now let's go further and take the consider our usual our usual production function. If we take the total derivative, we have this. Now assuming the v is equal to 0, just because it is a constant, right? It's an isocont, and therefore once the constant derivative is equal to 0, Then we have this equation, and from this equation we can manipulate and get what we have over here. And that is why the marginal rate of substitution is equal to what we have over here, which is equal to the ratio of what we have over here. And now this value is always negative, right? It's negative because of this negative sign, because F1 here is positive, F2 here is positive. We said that for a production function, if you increase the inputs, the output also increases. And therefore, F1, which is the first derivative, is always positive. This one is positive. And therefore, the negativity over here is ensured by the negative that we do have over here. Now, the next point is for us to determine the concavity or the convexity of an isoquant. You recall that we talked about the concavity and the convexity of a function in our previous lecture. So what we need to do here is to take the second order derivative of this, our first order derivative, and see whether it's greater than 0 or less than 0. So this is the second order derivative, which we can write in this form, and then we can write in this form. Okay? When we take the total derivative of this function, we get this. Okay? And because here we are using the total derivative here with respect to x1, and then here with respect to what? X2. So we need to see how this derivative will break down into. And I think it's more comfortable to take each of them in one after the other. We can take this first one first. And what happened is that, notice that from the equation, the first equation that we have, we can express the x2 in this form. Okay? So when we put this one into our equation here, right, into our equation here, we are going to have these two equations. And this first derivative gives us that, which we can more or less, simplify into what we have over here. When we go further, when we take the other derivative, it's going to give us that, and then which we can, simplify as we can see over here. And we also need to apply Young's theorem that when a function is continuous, the second order cross partial derivatives are equal. That is f1 is equal to f2 So when we make that substitutions and we go back to our equation, we can more or less satisfy ourselves that the second order derivative is equal to what we have over here. So to determine the concavity of this function or convexity will depend on the value that we have over here at the point of interest. If this value is greater than 0, then the isoquant is concave. If we have this value to be less than 0, then the isoquant is convex, right? Right, so this is an example that we did for a simple situation when we have two variables, right? In general, when we have a function in n inputs, and we know that the first order derivative is what we have over here, we can find the isoquant between any of the inputs using the formula that we have over here. And when the equation we have over here is greater than 0, then we have what we call a convex isoquant. And when it's less than 0, then we have a concave isoquant. So this is just a generalization of the situation that we have when we had only two sort of inputs. Let's look at an example. We have this function involving two sort of inputs, and we are supposed to determine if it is more or less the nature of the isoquant. So this is our function. We just have our conditions for the second order, which we have already prepared. There's a cooked formula that you can use. So when we take the first differential, we get this. We have come again the first order differentials over here. When we do it with respect to x2, we have this. And again, f22, we have this. And when we substitute these values into the formula, and we can obtain what we have over here, and we know that this value gives us greater than 0 because x and x1, x2 are always 0. And we have this one to be strictly 0, and therefore we can talk about strictly concave convex isoquant. The last thing that we would like to talk about is the elasticity of substitution. Okay, elasticity of substitution. And if we look at our function that we have been dealing with, right, and what we have to do is that we are more or less interested in finding a quantitative measure of the rate of, factor substitution along an isoquant, right? We are interested in finding the rate of how one input is substituted for other using more quantitative measure. And this is what we call the elasticity of what? Substitution. And we define this as the proportionate rate of change of the input ratio. This is the ratio of the input divided by the proportionate rate of change of the, marginal rate of technical substitution. So if you look at this, this is the formula for finding the elasticity of substitution mathematically. And for the simple example that we have, that in a situation where we have two inputs, this formula boils down to what we have over here. All right, this formula boils down to what we have over here. Those who are mathematically inclined can look at Afachan. He discusses how this formula, came about. And I think Dowling also provides something. The only thing is that we don't have much time to go into that. What we are going to do is to just have an application. Let's look at an example. So let's compute the elasticity of substitution for this simple, function. We know there's a formula for calculating the elasticity of substitution for a simple function with two variables. So these are the first order derivatives and the requisite derivatives. We know this is the formula. And if we decide to change through by using the appropriate variables that we have over here, and then when we substitute, we are going to get the elasticity of substitution to be 1. This is a very beautiful function. I will not explain why it's equal to 1. It's a Cobb-Douglas function, which I think as we go on, you will come to understand this function very well, and you know how this function behaves, this Cobb-Douglas function, which is well used in economics. So what I would like you to know is that for now, this function is a cooked function, a formula for finding the elasticity of substitution for a function of two variables. So whenever you are given any function of two variables and you know this formula, you take the first order, second order partial derivatives, you put in this formula and you are able to know the elasticity of what? Substitution. Now you can take this example. This function is called constant elasticity of substitution. It's a very nice function you can see over here. All right. And your task is to find the first order differential, the second order, and here too, when you take this function, as we did earlier, you try to find the elasticity of substitution, and then take also this function, which is a constant elasticity of substitution, and then you try to find the elasticity of substitution. Thank you very much.